This video is going to emphasize exercise number 2 from chapter 12. So let's go through question 1 first. In this one, we're going to circle all of the reactions that successfully yield parachloroacetophenone, which is this compound depicted right here. Okay, let's see. Let me find the cursor. There's parachloroacetophenone. Okay, and it's a given that the first reaction works. This is chlorine is an ortho-para director. And it's going to put this acetyl group in the para position. Okay, so this is a yes. All right, what about the second reaction? This group here, which is called acetyl, this electron withdrawing group and a meta director. Thus, this one is going to fail because it's going to produce metachloroacetophenone. Okay, this next one is an older reaction, but it's alkyne hydration. Recognize that this is a terminal alkyne. Alkyne hydration is going to be regioselective, putting the oxygen in a more substituted carbon. So this is going to work. This is going to produce the compound at the top. That's the methyl ketone that you get from doing alkyne hydration on this terminal alkyne. This next one also works. Okay, this is a two-step process. Recall that in step 1, this is the dehydration. And this second step is ozonolysis, which is going to turn the double bond that we generate in step 1 into a carbon-oxygen double bond, and that is the product of our reaction. Okay, the last one is a side chain oxidation. So if we have an ethyl group here, it's going to one of the carbon bonds on the side chain is going to be cleaved, but it's going to produce a carboxylic acid. It's not going to produce the methyl ketone. So this one would be no. Okay, let's look at the next question. Why is reaction A faster than reaction B? And this answer has nothing to do with steric effects. Okay, so what we want to think about is the stability of the reactive intermediates in this reaction. And of course, these are the carbocations that you get from attacking the carbocation. Okay, so we're basically going to just do this process right here, and don't forget that there's a hydrogen here, and there's a hydrogen at the point where the nitro group attacks in the second one. All right, so let's look at the carbocations here. This carbocation right here, the one in black, is the one that you initially form, okay, right here. But we can write resonance structures for it, okay, so we can move the double bond there. That moves the carbocation to this site right here. And we can do that same process again, and that moves the carbocation over here. Notice that in these two resonance forms that are shown in blue, we have our carbocation directly beside an electron donating group, which is a very favorable situation, okay? All right, so let's think about how that principle applies when we look at the carbocation that arises from B. Okay, so we're going to move arrows like this. Okay, all right, and we initially get the carbocation right here. Again, we can write a series of resonance forms by switching the position of the double bond to the carbocation. Here we are here. And in this last one, we actually put the carbocation directly beside the electron donating group. But notice that in the carbocation from A, there's two resonance forms that have the carbocation beside the electron donating group. And in resonance form B, there's only one. Excuse me. So this accounts for the faster reactivity of A. Basically, the carbocation in A has more stabilization from the OMe groups than the carbocation in B. Technically, The best carbocations of all would not be these carbocation resonance structures, but I'll just draw one of them right here. They would be the oxonium ion resonance forms that you get from this resonance interaction here, right? Okay, so H and O2, and we're going to have a carbon-oxygen double bond. Right there. Okay, so that would actually be the best carbocation resonance form you could draw, and you could draw a similar one for the other one. Sorry, I forgot to turn the email sign off. Okay, all right, let's look at the next problem. Suggested are 3 potential synthetic routes to 3-chloro-1-isobutylbenzene. Only one of these routes is going to successfully provide the desired product. Which one? And we're going to define the problem for each of those synthesis routes that we did not choose. Okay, so let's look at these one at a time. Okay, route A doesn't work. Doesn't work because in step 1 we do the Friedel-Crafts acylation. That's exactly what we're expecting to see. Okay, we're forming this product, but once we make this, we're going to reduce the carbon-oxygen double bond with a Clemmensen reduction to the corresponding CH2 group. But at this point, we have an electron donating group in our system, and this is of course an ortho-para director, so we're not going to get the right product. We're going to get the product where chlorine is either para as depicted, or it might be ortho. Okay, let's examine route B. Route B is actually the correct answer. Step 1 is exactly like it is in step A, but in step 2, the real difference is that we have an electron withdrawing group, and it's a meta-director. Okay, so when we do step 2, which is the chlorine introduction, we get chlorine meta to the original group that was here, and this establishes the desired regiochemistry that it's requested in the directions for the problem. And in step 3, we do the Clemmensen reduction, and this produces the desired product. Okay, route C is going to fail for a variety of reasons. Reason number 1 is that the carbocation that we have here is not a stable carbocation. It's a primary carbocation that could easily rearrange to a tertiary carbocation just by doing a 1,2 hydrogen shift. Okay, so that's going to be pretty much an unstoppable process. So it's going to fail in step 1 because we're going to put a T-butyl group and not an isobutyl group there due to the rearrangement of the carbocation intermediate. And it's also going to fail in step 2 because regardless of whether it's T-butyl or isobutyl up here, it's going to be an electron donating group or an ortho-para director. And thus you would put chlorine ortho or para, which is in the wrong place in the problem's directions, and you don't even put the right alkyl group on there anyway. So I guess step 2 is just adding to the, say it's showing off, right? But we don't really even need to consider step 2 if step 1 totally fails. Okay, all right. Let's look at the last problem. Suggest a sequence of reactions that can accomplish the following transformation. It takes 4 to 5 steps depending on whether you do add the nitro groups one at a time or just use 2 equivalents of the nitrating agent. Okay, we're going to use ethyl chloride as the source of extra carbons and sometime later oxidize the ethyl group to the COOET. So this group here, the carboxylic acid group, remember, is going to come from the Okay, there's the cursor. Sorry, I totally lost it. Okay. It's not very visible on this program. Okay. So the carboxylic acid group is going to come from a side chain oxidation that was discussed in the previous chapter. Let's analyze this. All of the nitro groups are orthopara to chlorine or COH, which and the COH used to be an ethyl group. This is a very happy situation because chlorine's an orthopara director, and when this was an ethyl group, it was also an orthopara director. So the nitros are in exactly the right place. Chlorine is meta to COOH, meaning it cannot be added while the carbon group is an ethyl group. Okay? And chlorine we're going to use to direct the nitro groups. The reason here is, we'll discuss this in the next slide, but if the chlorine's not here, where does it add when you do the chlorination? It's not completely clear because all we have on this is electron donating groups, okay, or electron withdrawing groups. Okay, so in our final step, we're going to add the nitro groups. Okay, so we're going to take 2 moles of nitric acid, sulfuric acid. These are going to go orthopara to the chlorine. They're not going to go here because this is a place that's between 2 meta groups. Okay, so 2 moles of nitric acid, sulfuric acid applied to metachlorobenzoic acid would produce the desired compound. All right, we need to add chlorine while this is the carboxylic acid stage because we need for this group, whatever group we have in the monosubstituted benzene, we need for it to be a meta-director. And it's a meta-director as the carboxylic acid, but as the ethyl group, it's an orthopara director. So we need to add chlorine while it's a COH group. Okay? Our immediate precursor to that is this oxidation with chromium-6 or manganese-7 applied to the ethyl benzene. And we're going to convert benzene to ethyl benzene using the Friedel-Crafts reaction. Ethyl chloride can't really rearrange to a better carbocation, so it's one of the ones that we're going to want to use in this reaction. Okay, all right, so this is in fact the best answer. It's written here, it's 4 steps. Friedel-Crafts, oxidation, chlorination, double nitration. It would be 5 steps if you added the nitro groups one at a time. Okay. All right, let's look at a common incorrect answer, and this happens because recognize that if it was the ethyl group here, it would be the dominant group. Chlorine and ethyl are actually sending the nitro groups to the same place, so it would seem to be okay in that respect, but there's a problem. Okay? All right, so let's examine that route. All right, so we're going to make ethyl benzene. Okay. Right here. We can't add chlorine yet because this is a orthopara director, so let's add the nitros. Okay, they're going to go orthopara. We'll just be very careful to add 2 moles of this reagent. We'll get a small byproduct where there's nitro here and here, but this should be the major product. We're going to oxidize at this stage, but here's the problem in this alternate plan here. It comes from this very last step here. All right, so where does the chlorine go when you try to do a chlorination here? We don't have any electron donating groups. We have carboxylic acid, which is not as electron withdrawing as nitro. We're going to say the regiochemistry would be totally ambiguous. It would probably go ortho. Okay, probably go here, because only when it goes here can you avoid putting the positive charge beside two nitro groups, but it's probably the regioselectivity isn't going to be very high in that case. Okay, so I'm going to stop this